Okay, we're going to talk about the global uncertainty problem. Um, let's try to articulate the problem. So there is a need in order to utilize PTP in a data centers, and actually, from what I concern, this is a valid requirement for any PTP deployment. The network architect, the infrastructure owner should know at any time what is the total error bound in the system. What is the most distant node in the system? What are the nodes that are not synchronized at the moment? What is the maximum error bound? And the idea is, first of all, to know it, and then to maintain problems and to mitigate issues. And then we also believe, as I believe Georgie will present, that there is a beneficial for application uh, to use this parameter. So it cannot be achieved easily. And the problem is that because within PTP, by the way, we distinguish between measurement and testing. Measurement is something that you do all the time with your production equipment, not with special testing equipment. This is something that's running all the time and you can monitor and measure. And currently what PTP allow you to do is to measure the offset from your own master clock. So each boundary clock, for example, will measure the offset, whether it's RMS or maximum, from his own master clock. So and the problem is what is the total error bound between the grandmaster and the least ordinary clock, or within all of them. This is something that cannot be achieved today with PTP. So what we think that will help this, of course, we always think in scale, and the solution has to be scalable. So the simple solution from our point of view will be to propagate the information, because when this boundary clock B will measure the distance from his own master at A, um, this information exists here. Now we need to propagate it downstream in the clock tree. So this boundary clock will add a TLV signal that will emphasize his offset from his own master. Now the next level in the clock tree will take this signal and accumulate this signal with its own measurement from boundary clock B, and then so boundary clock C will add the offset from B to A and the measured distance from C to B, and then it will signal the offset from A to D. And by that, theoretically, the network can grow to infinite. Um, yeah, I know the clock tree span demands um, require accuracy downgrade on every node, but nevertheless, regardless of how your clock tree look like, you can with this idea you can measure and calculate the error bound across every node. So now we have a much smaller problem. We have a problem that each node knows is distant from the grandmaster, and we just need to send this data. We can do it asynchronously to a centralized unit that will calculate the maximum out of it. Um, so with that, of course, there is some assumption about the period. It will not be strictly tied and measured as it is today, but we need to remember that also um, the PTP daemon measurements are not up to date. They are filtered and smeared. So it's okay to have, we assume it's okay to have windowing across several seconds. Second thing that needs to be done is to align those TLV signals periods with the sync announcement periods. They are not aligned, and we need to define them. So actually, this idea is as we say, is still in diapers. We would like you to help us and join the TAP project in order to complete the definition of this. We want to make it kind of maybe part of the profile, maybe a different specification on top of PTP. And in order to use it, we will test it in scale. So you have like a lifetime opportunity to test it in scale. And we, of course, any volunteers that will help us to test it in scale is more than welcome on more clusters. And then yeah, and we definitely need the community help here. That's it. It was short, a lot, I know, but
no, it was great. Thanks for explaining the problem, sensitivity problem, and the means to solve it. TLV is indeed where we are asking for everyone's help, either by contributing to the spec or by helping us test it, as Stefan mentioned. We already have some beta sites and we're looking for more. So please raise your hand or reach out to us. Any questions from the team?
Yeah, maybe I can ask a question. Dotan, how do you see, let's say, the TLV starting, let's say, from, let's say from WAN, like all the way from the time provider or something? Because I'm like, we can't do anything about the GPS. But let's say you're a grandmaster somehow receiving something, let's say, again, if we have this consensus running between, like, let's say, data centers, how do you see like this is like basically the future for this can be expanded to that point?
That's a very good question. I think that at immediate step, I would rely on what you emphasized, that each POP, each location will measure the distance from their own GNSS signal, and then we can add to this error the difference between the signals that are measured across location.
And another thing is like, Georgi is, I think, is Georgi on the call here?
Yeah, he is.
Yeah. So
yes,
like,
I'm here.
Yeah, let's say, for example, now, can you elaborate more on like how the TLV then is going to basically kick in like as an error bound going further, let's say, let's say with that like commit and wait?
I have a presentation for that, and I think the next one is.
Oh, so we don't want to
about-
spoil. No
Yeah,
spoiler.
that's the next one. But the error bound is compound from 3 elements. One is the network error, which now can be measured. And the second one is the PCI. And the third one is the application. So as I always say, the best engineering work is to put the responsibility on someone else. By eliminating the network problem, I put the responsibility now on Georgie to solve it.
So one more thing, that, Dotan, how do you think like the TLV can help, let's say, when we have this designated master clocks? Like now, like basically the boundary clock is becoming like more fuzzy.
That's right. We will need to correlate the designated boundary clock with the proper offset. That's right.
I
It's
think
gonna be, yeah.
it looks to me like the designated master clock DMC can take advantage a lot of the TLV.
Okay. I don't see it yet, but
No, I mean, it can take advantage of it because it will be great. Like, because then, you know, the error bound, I mean, boundary clocks, they can do it, they take advantage of this, obviously. But I see DMC can take more advantage of this. It's like, it's very, because in the DMC, like you have all these boundaries are very soft anyways. they're mixed up, like you don't have like a clear cut, like the same switches, like just the direction of the timing packets is basically determining which way they're going. So now having like a clear TLV in these machines can really help like overall for, let's say, the clients to know what is basically going on through the thing. Because again, in boundary clocks, you're expected to not have that much of variations. But let's say in a designated master clock, which is just like a normal host acting as like boundary clock, things change all the time. There's different loads. There's like
Yes.
congestion, all these things. So TLV now as a dynamic measure can perhaps be even more
Yeah.
critical.
You know what? I think it's a noble idea. The TLV can indicate something about the packet delay variation status.
Yeah, yeah.
Um,
And I think on top of that, what like as we're developing more in the DMC concept, uh, we again there is also a lot of polarization. Some people are hating it, and some are liking it. Typical to every technology. Uh, we're thinking that you can have like basically you don't bound it to one machine, and you have like the ability to go around between different machines, like round robin basically in that rack. So
mhm.
in that case, you can judge based on the TLV, let's say, if a machine can keep on a longer time that role due to a better oscillator, and or like vice versa, like a machine has like a relatively like let's say a lot of fluctuation in the oscillator due to the, let's say, the quality of the oscillator, or like I don't know, some temperature fluctuation based on, let's say, where it sits in the rack, or like the processing. Because remember, we don't want to take over the the job of the machine to become a DMC. DMC is just like a sidekick, like the machine is going to take over. Like it's just it's not supposed to be even any percentage of CPU load adding for this. It's just this machine is becoming a representative, talking to the grandmaster.
So so I tell you what confused me, and maybe it also can confuse our audience, but the solution is still valid.
Yeah.
Those designated boundary clocks will
Master clock, designated master clock.
designated boundary. The designated master clock, the round robin one, they will be round robin within the same rack or very locally.
Yeah,
So one should ask himself, wait, I don't expect any different temperature variance between them. But remember that once we signal the TLV, um, each one of them will know the packet delay variation and the error bound between itself and the superior grandmaster,
that's right.
which can allow us to indicate temperature or packet delay variation problems upstream in the clock tree.
Yeah.
That's right.
Yeah. So maybe it's not bad. Like let's say for the audience who are hearing DMC for the first time, I can go quickly through it. The idea comes from when we are trying to ramp up in a data center, like basically this whole time appliances project. It was like basically with this whole objective. We are trying to ramp up this higher, like better clocks into a existing data center. We have to deal with a lot of challenges, such as the implementation of the hardware compatibility. And when it comes to the switches, the PTP compliant, like let's say switches, which you have boundary clocks and transparent clocks. Transparent clocks looks to be relatively all in or all out. It means like either your ASIC can support it, which is great,
No, yeah,
just to
exactly.
enable it, or your ASIC cannot support it, then good luck. You have to wait for the next generation of your hardware changes, or forget about it. So
Yeah, it
now,
does.
Now again, transparent clocks, let's say you're lucky enough, your switches are capable to do that, great. You enable transparent clocks. Next in scale comes boundary clock. Why need boundary clock? Well, very simple. If you have only transparent clocks, you need to have basically the grandmaster talking to every machine. That is doable, but it comes with its own challenges. So let's say boundary clock is basically acting for scale, like one side again, talking to the grandmaster, the other side disseminating to more machines. Now, the thing is, like, implementation of boundary clock is definitely much harder than transparent clock. Reason is because now every machine has to implement the servo, and the packets have to basically be interpreted by the switch. Switch has to issue new packets going downward, let's say to downlink to the machines for dissemination and so on, new IP addresses, all kinds of things. So this becomes challenging, let's say, again, not impossible, but challenging. It might take a while. Meanwhile, you want to, let's say, prove the value for these systems. So you need an intermediate solution. So our team, we came up over TAP. Basically, we came up with this idea called DMC, Designated Master Clock, which in DMC, boundary clock is kind of the role of the boundary clock comes down from the switch back to one of the machines in the rack. So meaning, let's say, assume you have a data hall where you have, let's say, 5,000 racks. Every rack has something between, let's say, 50 to 200 machines. So that's like, puts you 200 to 1 million machines, and you have one grandmaster. So option one, you have only transparent clocks. You have 200 to 1 million machines, 200,000 to 1 million machines trying to talk to one grandmaster. Doable, but it can come with a lot of challenges. Like grandmaster, so many machines, and you don't have like enough, let's say, like the number of packets may go down because you have to go through so many machines and so on. So instead, again, let's say you don't have the option of boundary clocks yet. So what you do is you designate one machine per rack. That machine is going to talk to the grandmaster. Let's say in that example, you end up from 200,000 to 1 million machines down to only, let's say, 5,000 machines. And now that machine is going to talk to the other machines that are in that rack. So you do like basically the scaling now with just a normal machine that is sitting in that rack, acting as a representative for the machines that are in that rack, talking to the grandmaster. And this machine, we're thinking about like we can round robin this machine to one, you don't want to have one single point of failure. Two, you can always, with TLV and other measures, you can find out which machine has better, let's say, stability. You just dynamically are choosing which one has to go with that. So that was also another reason why we started the development of the open source grandmaster.
I want to connect it to the idea that you mentioned previously. We can measure and test it in scale thanks to the idea that the PPS can snapshot the PTP hardware clock, as this image illustrates.
Awesome.
Dotan and Ahmed, I have a question. Is there any limit to the scale? With the TLV solution, is there any limit to the scale or the depth that you can foresee?
So I think that any level of any node will add more inaccuracy with the measurement, and once we will test in scale, we will know how to nail it and to overcome it. So the answer is that we don't know yet.
These are the reason why Dotan is mentioning this way is because these are stochastic variables, and stochastic variables, they come basically with a mean and then, let's say, variance, and just adding them together is always challenging because the distribution and the alignment of them, things will change. But I mean, overall, you can have a loose definition of like, okay, now as you go further, this is your mean, this is like, let's say, your first delta in variance. So again, it's very early.
A similar approach took place in the ITU profile 8273.2 class C, where they defined the total absolute error for constant and variable in order not to accumulate them just like that.
Thank you.
Okay. Thank you for listening.
Okay, the next session starts in 8 minutes. So 9:55 by Michelle
Wonderful.
on PTP profile. You can sit tight until then.
Maybe we can answer any question is coming from the audience. Anything, Elad?
So far, no questions. Thanks for tying these two presentations together, Datan and Nachman, the visualization of the PPS in scale and how it scales for accurate measurement is very well articulated. And we do encourage others to follow and share with us their measurements. Thank you.
I can also add to this that we've been working also on like the frequency you're running your servo in is usually just a constant speed, and you just like basically taking advantage of this data plane, the power of the data plane in terms of speed, and you're just constantly like just going through your synchronization with your let's say grandmaster. So what we've been looking into, it's still in early stages, we're looking at a dynamic rate that you basically define now the range you want your clock error to be there. So you can continuously like monitor the values, but you don't do the adjustments. And you only do the adjustments when you reach, let's say, a certain, again, like basically the state machine of the PTP servo. We're trying to make it a little bit more dynamic. This gives us, let's say, a better chance for holdover because you're doing less changes and more moderate changes. And two, it can give us a overall indication of the health, let's say, of the oscillator, these local oscillators that you have, let's say, in the mix, to see how they're performing. Again, as Dotan mentioned, this question may come up all the time, like, okay, why there's a difference, let's say, between all these machines sitting in one rack. Actually, there's huge difference because there is no heterogeneous like workload on them. So things change all the time based on whatever like the CPU load is on these machines, let alone the fact that just being in different locations of the rack can give you a lot of variations of temperature and airflow.
Thank you.